Okay, hiya, I'm Olga-Joan Ktenidou. Okay, I'm blind now. I'll start with a short presentation about kappa at Diablo Canyon. So, as some of you know, there's only like 3 records at the Diablo Canyon station, so we tried to find a bit more data than that. We dug into the NGA was still flat file for these 3 events, and we kept all the records from stations on hard sites, so VS30 more than 500. DCPP is on VS30 of 1100, but we're not so lucky, so we're working with kind of softer sites there. We got the distances from the Diablo Canyon site, and we kept everything within 100 kilometers. We were going for something short, like 50, but again, we weren't so lucky. This is what the magnitudes and distances look like. So I've noted these 3, which are the actual DCPP records. And then you have this one other record at actual rock, so 900 meters per second, and then the rest are kind of softer. So this is a VS30 plot for you. So this is DCPP here at 1100. Then you've got 1 and 900, and all the others are just within the NERC category. So if we take into account the sigma given in the NJ with steel flat file, that takes give some thought as to whether the VS30 is measured or, well, the VS is measured or inferred. Then the scatter is so big that, yeah, all these guys are just NERC class C, really. So these are the 3 events we have to work with. Diablo Canyon is right here. And we have 16 stations, and each of them only recorded 1 event, except for the Diablo Canyon itself, of course. So this one's San Simeon. Then you have Parkfield, which got the most, and then Deer Canyon. Just a quick reminder about what we're talking about. So we're going to be looking at kappa in the traditional sense, so according to the definition of Anderson and Hoff. So we'll just be calling this kappa acceleration slope, and we just measure it off the high frequency slope of the acceleration spectrum on log linear scale. We do that on, we want to do that on lots of records at different distances in order to try to get to the 0 distance kappa, which is what we're after right now. That's because the 0 distance kappa, or kappa naught, is what characterizes your site. And mainly we're just trying to clean it up from all the path effects, so from the Q effect there. This is just a look at the data. This is just a stack of noise acceleration Fourier spectra. So we've got tons of different instruments, different Nyquists, different levels of noise. What they have in common is that they're pretty good up to maybe 40 hertz. So we're going to work to up to 40 hertz with the data. This is just all the records available. And we're going to work with bandwidth for which we have a good signal to noise, so around 3. This column here shows that for most of the records we don't have either no pre-event noise or almost not a good one, so I picked off the coda, or worst case off the P-wave, to do that. I need to say that all the data processing was done by Tadahiro Kishida at PEER. Yeah, so we go on with the green bits, which give a signal to noise over 3, and this is an overview of all the high frequency slopes of which we got kappa, and this is just an idea of the frequency range we're gonna work in. So it's well, on this edge it's kind of dependent on the noise, and on this edge it's kind of dependent on the magnitude, of course. But it's more or less between, say, 10 and 25 hertz. And if we just stack all the kappa measurements and look at it with distance, this is all the data we have. So after Nico's mind-boggling mathematics, this is what I'm showing, so a straight line. So this is really simple. You can bring the kids. there's not really heaps of data to justify going for a much more complex model for frequency-dependent or depth-dependent Q, but if we just draw a straight line through here, we get a frequency-independent constant Q of around 570, and hang on to the number because we're going to check on it later, and you get a kappa naught of around 47 milliseconds, of course with quite a big sigma around it, so around 15 milliseconds. If you don't trust this simplification, I have another one for you. So if you just go out to 15 kilometers, there is no Q effect, so no distant trend to all the data, so you can just average all together and get your kappa naught that way, and that'll give you the exact same thing. So either way, you have around 45 milliseconds of average kappa. This is just showing the different paths for event 1 and event 3. Yeah, colors are not showing really well, and in any case, that doesn't matter because it's just to say that the different paths sampled by the waves don't really help us sort out the scatter lot. So the only thing that remains to look at is how does the oversimplified Q work out with other independent estimates of Q. So if we use a typical power law relation for the frequency-dependent Q in the Western US, for the frequency range that I show you we worked in, the Q is like, wrong button, is around 500 to 1,000. And then if we use the really elegant results that Kevin presented yesterday, this is the map of the US, and you are here. So if we blow this up, we have around 600 to 700 of a Q in this neighborhood. There's an issue of saturation of the color scale here, so we might actually be perhaps even down to 400, but more or less 600 is spot on the number we got from the first simplification of the slope. So even if this is LGQ and we're going for S waves, it makes sense, kind of. So we're kind of okay with the Q. The kappa knots, on the other hand, we can look at with respect to the site conditions we have at each site. Given the sigmas we have, we can't really look at the individual kappas versus VS30 because this is just a big mess. So I'm just gonna plot NERP B sites in brown and NERP C in green, which I just realized is exactly the combination of colors that colorblind people can't see, so I'm sorry. So these guys here, and these guys here are brown. And yeah, half the men probably can't see that. Okay. So these plot in a nice straight line, but they plot kind of higher than a lot of their green friends, and that shouldn't really be so. We would kind of expect them to plot kind of lower. The Q trend is good, but it's like the kappas are kind of inflated, so I was wondering why. And maybe one explanation is some high frequency amplification effect at the hard sites. Well, Paradai and Bindi explained that nicely in their paper. So what I did with the MPO data we dispose of is I got the 3 records from the DCPP and just did an H over V ratio with the S-wave Fourier spectra. And what you see is this line is 1, so no amplification. So what you have is like relatively broadband amplification up to maybe 8 or 10 hertz, and after which you have a sudden trough down to 20. And the window is to show you the bandwidth in which we computed kappa. So I think there's a good chance that the kappa value of 45, well, yeah, it is 45 more or less for the stiff sides too. I think it's kind of inflated because of this. So I think that the kappa naught for Diablo Canyon should lie kind of beneath that. This is just a glimpse into what's to happen next at DCPP for kappa. So With the data I showed, we're going to try and do inversions using the entire frequency band. So I discovered yesterday that the profile beneath Diablo Canyon is available, so if we can try to extract the site amplification from the spectra, then we can maybe get a kappa for the real rock. And I have no idea if Norm wants to talk about this, but I just put a couple of plots there because I think it's in his future plans. So if you need it, it's going to be here. And that's it for Diablo Canyon.
So let me add a couple things, is that the data set Olga used starting at Pier to say which earthquakes in the Pier data set are in this region and have high velocities, and that's why you run out of data quickly.
Really high, yeah.
Right. I know that there are going to be other events, probably smaller, and Yusuf, I forget what the cutoff was for the small magnitude data, but we focused on magnitude 3 and well recorded, right? And I think for this area, we need to relax that a little bit, maybe go down to 2 and not so well recorded to expand what Olga's doing from this few samples per earthquake to a much bigger data set.
Absolutely. That's a very good idea. In fact, we want to try even in the other parts of the country and world.
The thing is, there was nothing at a distance of less than 80 kilometers from the site, so we were just working with far away.
Right, but that's what was in the Pier set.
Yeah,
and I think when we go to
the lowest is like 3 point.
The regional data center, there should be more in there than that. So I think we can add to this along the Central Coast area. Because Marcia showed the other day that network, so those stations are there. They are all in the regular data center, but I don't think they met the criteria that Pier used, first of all, to add in earthquakes, because we wanted magnitude 3s with like 20 or 30 recordings to have them. I think that's really our issue.
So that'll make a rich data set.
Even richer, which is really what you need. And then the VibraSize data we talked about last time, I shouldn't say VibraSize, the geophone data from little earthquakes that happened during our onshore sampling, and that's something that we're going to, all of those start to address. Part of the reason why Olga has only gone this far is we put her on the Arizona kappas, right, to focus on that.
You knew it was going to be more fun.
Yeah. Comments or questions for Olga? Yeah.
Hi, Olga. Can you go back to your kappa versus distance? Yeah, this one. It kind of seems like if you were to ignore those points, you'd have a steeper slope and a smaller kappa zero. I mean, do you have any thoughts about that?
If you go out to
like
30.
40 or something?
If you just cut it off here.
Yeah.
Yeah,
Because
I think you would get a really big sigma on the slope with that. Like, I think it would give you like quite a small coefficient of correlation. And I don't think I'm gonna believe that the regional Q is this. I think this is gonna give you like
kappa of
7,000
on rock. You'd better have
This will
an
give you
explanation.
7,000, and yeah, the kappa knot will be here. So I think it'll be kind of biased.
Yeah.
This comes back to what is kappa and where is it coming from. And the Central Coast is a beat up area, right? I mean, it's fractured, and so it's melange. So kappa is the waves are seeing the effects of all of that fracturing, even though you may be on a little hard piece within that melange. That's probably, kappa is not as well correlated with VS30 in this region as it might be in other parts of the world. That's kind of what she's finding. There are no 0.01 kappas there so far.
Okay, and I think also maybe a couple of years ago, Katie showed numbers very close to this, right? I think in Diablo Canyon workshop.
We had a kappa of 0.042.
Okay.
But those are the same ones she's working with.
Oh, it's the same.
So I thought these were shockingly high for me. So what I can figure from that is maybe it's amplification. I mean, for a 500 meter per second site, I mean, this might be fine. But then finding the 1100 meter per seconds here, I think if these are moved down here, then it'll give you like an overall 30 rather than 42 or 45.
But it's suggesting kappa is not just VS30 dependent. There's something else that's a major factor that we have to keep track of.
Yeah, but that we know.